Yes, it works. Okay, we are at the point to discuss the mass transfer limitation, and I just show you that you can solve this very difficult second order partial differential equation under steady state and get a linear variation of the concentration between the electrode surface and the bulk. There's an approximation. This approximation is not so bad because if you solve this equation with the correct boundary conditions, you get the dash curves here. So in the main point close to the surface, it works well. So this solution can give you the concentration gradient here, and you see if with the boundary condition it's okay. For x equals 0, you have the concentration at the electrode surface, Cy0, and for x greater than the length of diffusion, x equal delta, you get the bulk concentration. Okay, so it works. And then you can see that you can reach a limiting current or limiting current density, because when you consume all the species arriving at the electrode surface, the surface concentration Cy of 0 going to 0, that's the limit, and then you have the maximum slope, the maximum gradient, so the maximum rate of transfer. Okay? That's very easy to follow. And this process does not depend on the electrode potential. That means in the curve, if you see some limiting current, independent of the electrode potential, that's mass transfer limitation. And now you can get the limiting current density here. The current density is times NF times the gradient. At the limiting, this concentration at the electrode surface is 0, so you get the limiting current density, NF times diffusion coefficient times the bulk concentration, and you can make the ratio between the current density and the limiting current, which depends only on the concentration, and in that way you can calculate the concentration at the surface, or the pressure at the surface relatively to the bulk concentration or pressure. It is 1 minus the absolute value of the current density divided by the limiting current. I put the absolute value because you know if you have an adiabatic process it's positive, the cathodic process is negative. So be sure to count correctly the current density, you put absolute current. And then you can have a limiting for a very, very fast electrochemical reaction. The charge transfer reaction is very, very fast, so the overall kinetics will be limited by mass transfer. So at the electrode surface you need equilibrium, electrochemical equilibrium. It means that you have the Nernst equation applying at the electrode surface under this condition.
How does temperature play a role here? I guess is that temperature increases diffusion, right? So
yes, yes. At temperature, you have two terms. You have the temperature, you have the temperature with RT, and you have the temperature in the diffusion coefficient.
So the diffusion increases with
yes.
temperature, but
yes.
the efficiency goes down with temperature, increasing temperature. Huh?
Yes. For the diffusion coefficient, normally you have some exponential minus activation energy for diffusion, of course. Yes. But it is not so important in that case. Because for pale fuel cells, we work between ambient temperature and 70 degrees. So it's not so important.
Not significant?
Not significant, yes. Okay, so you get what is called concentration over voltage. Concentration over voltage, that's the Nernst law, where the concentration taken as this quantity 1 minus the ratio of current density as limiting current density for the anode and for the cathode. So that's the second term which will limit your process, your overall kinetics, mass transfer limitation. Okay, so you can see how it is with curves. If you draw this curve, you can theoretically calculate the current density versus the cell voltage for what is called Tafel slope. That's more or less the slope for the electrochemical process, 60 millivolts per decade. You can choose a given current density, limiting current density, 1.4 amps per square centimeter. So you see, you have the limiting current density, and you start to reduce oxygen from 1.23 volts. Then you are beginning with exponential behavior because it is limited by electron transfer. And for higher current density, you reach the limiting current density due to mass transport of oxygen, for example, and you get that curve. It is a sigmoid curve, and then if you plot the cell voltage versus current density, it is the same curve, but you turn by 90-degree angle the curves, and you get this characteristic, which is due to mass transfer limitation. Okay? So now, if we look at all the process, we can say that all the overvoltage, activation of overvoltage, concentration of overvoltage, because we have a series process, they add together as a first approximation. Okay, so if you calculate the cell voltage, including some ohmic losses due to the electrolyte resistance, electrolyte interface resistance, the cell voltage is the difference between the cathode, the positive electrode, and the anode voltage, negative electrode, minus the ohmic drop. You replace this electrode potential by the equilibrium at zero current, and minus all the overvoltage, so minus activation of voltage due to electron transfer, minus concentration of voltage due to mass transfer for anode and for cathode, and then you subtract also the ohmic losses. So that's the general equation, which is more or less approximation of the cell voltage versus current density characteristic, electrical characteristic, which is very important for any electrical device, for a diode, for a semiconductor, for photovoltaic process. This is very important. And to get this relationship, which is relatively complicated, because you will have a problem and you don't have any document with you, I suggest that you can write all that in your textbook, in your sheet of paper, to make my problem if you have a problem. So the last equation, it is an approximation, and I also write here with minus not to be confused. Here you have G square over the fraction bar, but here you have G square over the fraction bar. So you reverse, you change the sign of the logarithm. And I just put minus, minus, and minus to be sure that you subtract every contribution of losses, I would say, of voltage losses and ohmic losses. So this equation could be a good approximation for the characteristic. And here I write the complete Butler-Fulmer equation. You saw that with Ludwig yesterday, with the part of mass transfer and some limiting behavior for smaller voltage compared to RT over NF. You have a linear relationship. It applies to hydrogen electrode, if you remember my first curve, around zero potential. You have the hydrogen electrode, it's nearly vertical on the graph, and it's like a linear, so it means that the overvoltage is equal some resistance times the current density and the resistance as a charge transfer resistance. You can continue the calculation. I'll just give you that as an idea. And for another limiting point, if you have a large voltage, you have an exponential behavior, and thus, if you take the logarithm that has a inverse function, you get the Tafel behavior. So Ludwig gave you the Tafel behavior also yesterday, and if you have very fast transfer reaction, the current exchange current density going to infinity, then you get the next equation. So in all that, you can play with all these equations and try to solve my problem. Okay, I don't see anymore. Now we go to the application of this relationship. That's an experimental graph giving the current density versus the electrode potential. We took the absolute value to have on the same graph the oxidation of the fuel, hydrogen or methanol, and reduction of oxygen. You have to think that oxygen reduction is a negative reaction. Normally it's like that. But I take the absolute value because in the circuit, if you have the same surface area, you must have the same current density, the same intensity of the circuit, and you must draw a horizontal line on the graph. For example, for hydrogen electrodes with this horizontal line, you get the anode potential, which is close to the equilibrium potential because it has a very fast reaction. And for oxygen reduction, you get that point. You have deviation from the standard electrode potential because of overvoltage. So the difference between this point and this point is the same voltage. So you can calculate the same voltage for each current density. And you can calculate, you can draw this curve like this one. Cell voltage versus current density. I also put methanol because if you have direct methanol fuel cells, you have a very large overvoltage at the anode also. So for the methanol, for example, with 200 milliamp per square centimeter, you have only 0.3 or 0.5 volt cell voltage versus 0.7, 0.8 volt for the hydrogen oxygen electrode. So you see the difference because the activity of methanol is lower, much lower than that of hydrogen. So hydrogen is the best reactive species, but the problem is a gaseous species. You must have storage, you must have a tank. Methanol is or ethanol, very nice to store because it's liquid, but the activity is smaller. Okay, now that's some theoretical curves using this equation. So for different case, you can calculate the cell voltage for different parameters. So there is a variation of the resistance, electrolyte or interface resistance, and you see if you have if you divide by 2 the cell resistance in ohms per square meter times square meter per centimeter. In that case, you have vector curves, the blue one, and at 0.7 volt, the current density is increasing from 0.25 to 0.4 amps per square centimeter. So you improve the energy efficiency and you improve the power of the cell. And between this curve and the green one, we change the current exchange density from 10 to minus 8 to 10 to minus 6, and you see the effect. It's a translation of the curves upward. And with the same slope, it means with the same electrolytic resistance. So this part, it comes from the activation charge transfer of the voltage, which is related to the exchange current density, and in that case, 2 order of magnitude at 2 times 60 millivolts per decade, so you have a shift upward of the curve by 120 millivolts. So that's the effect of the catalyst, the activation of a voltage. And the last point, that's the limiting current density, the effect of mass transfer. So you see that if you increase the current density from 1.2 amps per ampere per square centimeter to 2.2, you displace this vertical limiting current density to higher current density, and you improve again the cell voltage versus current density characteristics. So the main point to improve the fuel cell stack and to improve the elementary cell, the characteristic of the elementary cell. So you have to play the catalyst, you have to play with the membrane thickness, membrane resistance, interface resistance, and you have to play with the diffusion layer, because the reactants, they pass through the gas diffusion layer. You must avoid any limitation of mass transfer by the gas diffusion layer. So from technological point of view, there is a lot of work, of progress to do in that field. This field, better catalyst, better membranes, and better gas diffusion layer. So it's a mixture of technology and knowledge. So to illustrate that, one step by one step, with experimental results, I will show you the next. Before, excuse me, we can calculate the efficiency, which is very important. When the fuel cell is working, current density different of 0, the cell voltage deviates from the equilibrium cell voltage at 0 current. You have a decrease due to the overvoltage. So just recall, anodic overvoltage positive, cathodic overvoltage negative for the oxygen reaction, and these make decrease of the cell voltage. And if you have also electrolyte interface resistance, you have ohmic losses. So because of these losses, you have a working cell voltage which is much lower than the equilibrium cell voltage at 0 current. So you can define what is called the voltage efficiency. Voltage efficiency is the ratio of the working cell voltage by the equilibrium cell voltage. You can make the calculation like that. If you take the example I gave before, I just focus on the cell voltage, working cell voltage of 0.7 volt. So you have 57% cell voltage efficiency. Okay? And I had also something which is called Faraday efficiency. Faraday efficiency is related to the current density you can get, to the maximum current density according to the overall oxidation process. And it is related to the ratio of number of Faraday per mole experimentally you can get compared to the theoretical one. Okay. Give you example. For hydrogen, it's very easy. Hydrogen gives you 2 protons, 2 electrons, number Faraday is 2, number Faraday experimental is 2, number Faraday theoretical is 2. So this figure is nearly 100%. So you see, oh, excuse me, you see here the figure 100%. Now I go to methanol. I give you an example of the direct methanol fuel cell. In methanol fuel cell, it is much more difficult. Complete oxidation, you get carbon dioxide, 6 protons, 6 Faraday per mole. But if you stop at intermediate step, means you can get formaldehyde, formic acid, then CO2. Each step, 2 Faraday. So if you stop at the, let's say, formic acid step, you use 4 Faraday, versus theoretically 6 Faraday per mole of methanol for complete oxidation. So in that case, the Faradic efficiency will be 4/6, 2/3. So you decrease your efficiency by 2/3 because you don't use all the energy of the compound, of the methanol. Okay? Then you can get for the electrochemical cell the working efficiency, the number of Faraday experimental exchange times the cell working cell voltage, and you compare to the heat of reaction minus the variation of output. Make some easy calculation, and you get that the working efficiency as a product of the theoretical reversible efficiency times the voltage efficiency times the Faradic efficiency. Okay? So now for the hydrogen oxygen electrode, if we take the theoretical efficiency in the liquid state, with a high heating value, you have 83%. Then, with the cell voltage working at 0.7 volt, you have 57%. And for the Faradic, it's nearly 1. So you make the calculation, you have 47% of HP, of practical efficiency for the fuel cell. So you see the difference between the theoretical and the practical. So you have nearly factors 2. But you can compare which is you can get if you make cogeneration, combine heat and power. If you use the heat of the fuel cells, you can generate electricity in cogeneration. And that process.
What range of heat are we talking about?
That's a good question.
Is it enough?
I don't know what to answer about that. We can discuss. Okay. So you are right. That's a good question. But what can you see that if you use the electrical energy and the heat, you can get efficiency between 80, 85, and 95%. So it's very, very high. Okay, just give you an example for I say 100 kilowatt fuel cell for a car with
100 kilowatt?
yes, for a car. You have about 40 kilowatt of electrical energy, 45, and you have 50 kilowatt of heat, a little bit more. So you have to exhaust the heat for the car. So it's very difficult. But it's good, you can have good efficiency. But now if you take internal combustion engine, 100 kilowatt, you have 1/3 at maximum of the mechanical work, I would say 30 kilowatt or 20 kilowatt, and 1/3 as exhaust goes to the air, and the other third is changing with the radiator, the cooling radiator. So you see, with the fuel cells, we improve the efficiency because we don't have exhaust like the exhaust pipe. We just have cooling. But cooling is a cooling a car. If you have 50 kilowatt to exhaust, it's difficult. And for cogeneration, you must have a higher temperature for better cogeneration. Okay. Okay, now for yes. Bon, just the elementary cell, the pen fuel cells. Okay, you have different parts, different layers. The most important part is, the most important part is the membrane electrode assembly. So you have the membrane on both sides of which the electrode are pressed the catalytic electrodes. You have gasket for tightness of the system to gases. You have bipolar plates to connect different cells in series. And if you have only one cell, you have end plates. Okay, that's the basic scheme of elementary PEM fuel cell. The most important point is the membrane electrode assembly, which consists of the proton exchange membrane, Lafayette, for example, proton connecting membrane. You have the catalytic layer on both sides, and then you have the gas diffusion layer. you need gas diffusion layer to distribute the gases, either hydrogen or oxygen, to the catalytic sites, and you need also contact with ionic membrane with protons. So you have a three-phase boundary. You must have electrons, you must have protons, and you must have reactive species, hydrogen or oxygen, this layer. So you have the thickness, more or less, membrane about 100 micrometer, the catalyst layer, catalytic layer 10 micrometer, gas diffusion backing, gas diffusion layer about 200 micrometer. So altogether you have half a millimeter. That's important. And the shell voltage could be between 0.5 0.9 volt. This thickness is very important because if you make a stacks, you like to reduce the volume and to reduce the weight. So you must have very thin bipolar plates. This is the most important point where you can gain weight and volume. So just now the same curve, but the effect of the specific resistance. We call specific resistance the resistance related to 1 square meter, 1 square centimeter, 1 surface area unit, because it has heterogeneous process depending on the surface area. So if we take these curves, we can see that if you divide by 2 the specific resistance from 0.3 to 0.15 ohm square centimeter, you improve your characteristic, and at given cell voltage you increase the current density. Okay, just to recall the same curves as before, and now look at the experiment, some curves. There, before looking at the curves, we can discuss about the membrane. We don't discuss too much about membrane, but the membrane, which is the most used as a DuPont Nafion. This membrane, which has a polytetrafluorine backbone, PTFA. PTFA, it's a common commercial product. If you make cooking, you have on your plate some. Yes, yes, exactly. So you have PTFA. So it is very common, but it is either completely isolate. It's on that insulator. So we have to make conductivity to the membrane. So you have a bonding chain, and the bonding chain is with carbofluoro, and you terminate with the sulfonic acid. The sulfonic acid has the property to release protons. The acid releases the protons, and the sulfonic group is linked to the bonding chain and linked to the PTFE. So in this material, polymer material, you have a fixed backbone, ReFSO3 minus, and you have mobile protons. So the conductivity is due to this mobile protons. But it is much more complicated, of course. Just a simple idea. Because the proton usually is solvated by water. It's a very strong solvation process. So you need water to have a free proton. So it means that you have to humidify the membrane. So in the process, the system, you have humidifier because of that.
Does it as hydrophobic as Teflon?
Pardon me?
Is it as hydrophobic as Teflon? Water repellency?
No. It's hydrophilic.
Is it hydrophilic?
Yeah, because of this part. That's very hydrophilic because of the proton.
Very
But in fact, you have some cluster difficult. Yes, the structure of Nafion is relatively difficult. You have some. Yes, yes. You are hydrophilic and hydrophilic. You
What
have
is
two
the
parts.
contact angle when you measure?
Good question. I cannot answer. I cannot answer.
Excuse me, what was the yellow part of this?
Alors, ok. Alors, okay. That's DuPont Nafion. So you have relatively long chain, and if you have if you shorter the chain, the short bonding chain, you take off all this yellow colored atoms, carbon and fluor, and you get that structure So it is shorter. It means that you can have a better conductivity, because the conductivity is times the number of free charge times the mobility. So the mobility of proton will be better in that. And there are many attempts in the literature, many laboratories, academic laboratories, industrial laboratories, government laboratories, to have other polymer structure which are better than Nafion. But until now, Nafion is the best for application. Yes. No chance to escape. So, no chance to escape to Nafion. So some experimental results from Ballard a long time ago. So 3 different membranes, Nafion 117, Nafion 115, and the Dow membrane. So 117, 115 means Nafion with equivalent molecular weight of 1100 and 5 or 7 was the thickness of the Nafion in mils and 1,000 of inch. So you can calculate 25 micrometer per mils, so 5 times 125, 7 times 175. So if you decrease the thickness, you decrease the specific resistance, because you see the specific resistance is directly proportional to the thickness. So you improve. And if you increase the conductivity, the resistance, specific resistance is also decreased. So you can improve the curve just by playing with the conductivity and the resistivity or conductivity. So it is an important point to decrease the thickness, but you have to keep the tightness to gases.
Yeah, tight, gas tight.
Gas tight. But if you have mixture of hydrogen and oxygen, you have problems. It happens sometimes. In bad laboratory it happens. In good laboratory, no. Okay, so that's a very important point. The next point is to discuss the limiting current density. Again, with 2 examples of current density, 1.4 amps here and 2.2 something here. So you again improve the cell voltage current density characteristic, and you compare that to the literature, and for the main point is the diffusion of oxygen in the gas diffusion layer. So the gas diffusion layer is some trick, it's difficult. It's a technological approach. You must have some secrets on how to know to do the best gas diffusion layer to avoid mass transfer.
Some secret. Must be
Some secret, yeah, sure. So I don't give you any
open secret or
open secret, of course. Like for us, we say secret, but you say to your neighbor, I have secret. Don't tell us. Don't tell anyone. Don't tell to anyone. That's it. You will go to his neighbor. I have a secret. Don't tell.
Your business.
That's academic secret. No, okay, just joking. So you see the difference between 3 gas diffusion layer with microporous layer coated, and you can impregnate it with fluoroethylene polymer with 30 weight% or 10 weight%, or all that is to have layer which is sufficiently solid, and you must control the permeability to gases. You can add poroform, etc., etc. So the main point is you see the effect of the limiting current density. If you improve the mass transportation inside the gas diffusion layer, you have better current density, 1 amp per square centimeter. So all the trick in this curve, all the trick you can show experimentally some example. Okay? The last example is the effect of electron transfer over voltage. That's the effect of the catalyst. If you change of catalyst, you can change the change current density. That's where the catalyst is acting like the exponential minus activation energy, which depends on the catalyst. So you see, if you have a current density changed by 10 to minus 8, and you go to 10 minus 6, you shift the curves by 120 millivolts per decade, so you improve greatly the characteristic at 0.7 volt. Your current density is going from 0.4 to 0.9. So you have an increase of the energy, specific energy, specific power. And experimentally, I will give you example from the direct ethanol fuel cell. Why I took this example? Because with hydrogen electrode, the reaction is so fast, you have nearly no effect of the catalytic material. The only effect is you have to diminish the quantity of platinum, which is the other trick. So you have two tricks in the PEM fuel cells. You have the membrane, graphene is a trick, and platinum is another one.
Another trick.
Yes. So, yes,
wires.
Nanowire or nanotubes and so on. So you have to decrease the quantity of platinum. For hydrogen, there's no problem. For oxygen, that's a big challenge to decrease the overvoltage by choosing a good catalyst. But only a miraculous catalyst is platinum. But you can make platinum plus something. You add other metals, binary, ternary system, metallic system, and you can improve a little bit, but not that much. So with ethanol, oxidation is a very difficult reaction, so the effect of catalyst is much more important, so why I choose that? So I have the cell voltage versus current density curve for different catalysts, pure platinum and the platinum tin, platinum ruthenium, platinum molybdenum. So you see that with platinum tin, you have a very large shift of the curves upwards. So you play on the current exchange current density strongly. But this one platinum is bad because you decrease. You can also draw the power, specific power, milliwatt per square centimeter versus current density. You make multiplication of the current density by the cell voltage, and you have the power. And you can draw that curve. You see the effect of catalyst is very, very important. That means. Okay.
Can we have a question?
Yes, sure. Yes, we can discuss.
You have given various examples on the membrane, electrode, and so on. What about the interfacial interface between the membrane and the electrode, and what is the role is played here? Because we were discussing in the morning about the use of liquid nephron to seal or to bring a close contact between the membrane and the electrode. How can we play with that?
Okay. Well, did you follow the question? It was the question is about the interface between the electrode and the membrane. In fact, well, I have no transparency on that. In fact, the electrochemical reaction is an interfacial reaction, but if you have only one surface, it's very limited. So we have to develop the surface. So it means you have to go from 2D surface to a 3D volume. So you have to develop some mixture of interface in a 3D, in a volume. So in the volume you must have catalyst, you must have electrons, you must have protons, and you must have the writing species. So it is called the three-phase boundary for the electrochemical reaction. So the idea, as technological point of view, you must develop the three-phase boundary in a volume. So you mixed naphthalene, liquid naphthalene, with a catalyst layer, and with some binder and some many things, and you paint your electrode, gas diffusion layer and catalyst layer with ink, and you pressed on the membrane by increasing the pressure and temperature. So pressure, hot press, yes. So the trick is to make hot pressed membrane electrode assembly. So there is a lot of knowledge, a lot of technology in that, because you can have different additives have good contact. So those are the points. Is it okay?
Yeah.
But I have
Later we
no.
want to see how the electrochemical reaction go at this particular 3D.
Yes,
Later.
right.
Later is okay.
Okay. Okay, so just we go very fast about that. About example. So one point which is important for fuel cells is they can work in a very wide range of power. From I put 1 watt, but you can put 1 microwatt to 10 megawatt or gigawatt, with more or less a similar energy efficiency. It's different with conventional power plant, because if you are a larger plant, you increase efficiency. But for fuel cells, more or less, you have the same efficiency for very low power or for high power. Okay? So you have application in many fields: electric power plant, electric vehicle, auxiliary power unit, aerospace, household, portable, etc. Okay. So just shortly the application.
Is there any known example for megawatt plan for power for
Until now, the PEM until now the largest experimental fuel cells was the phosphoric acid fuel cells, which was experimented by TEPCO. Fukushima. Yes, TEPCO, they own the Fukushima nuclear power plant. But in that, yes, 15, 20 years ago, they experiment a phosphoric acid fuel cell power plant of 11 megawatt. That is a schematic of this power plant. I think that's the biggest experiment. But the good point is, at the beginning of the experiment, the overall efficiency taken naphtha or natural gas to electricity to the grid, so the alternative is AC current, alternative current, was 41% at the beginning. And after 2 years of operation, it was 39%. So very, very small decrease of the efficiency during working 2 years. So that's a good point for fuel cells.
Based on limiting current density, I made a rough calculation. It's about 1 watt per centimeter square. Is it correct?
Yes.
Roughly?
Yes, okay. Yes.
So this is pretty good actually.
Yes.
So
Yes.
that device there is like 30 watts around? That device there?
Yeah.
Perhaps, is it correct?
I don't know about that.
So for that is 30 watts, is not so how many? I know, it's not correct.
Okay.
Even it is half watt per centimeter square.
Household application, 1 to 10 kilowatt. Now in Japan, there are many small fuel cells, 1 to kilowatt, about 1,000 fuel cells, manufactured, distributed among people, and was a good figure. They have electricity and heat. Okay. The fuel cell car, Necar Class A from Mercedes, it works. At that time, 400 kilometer range with liquid hydrogen, but now you have a compressed bottle. Yes, I'm sorry, the pointer is not working anymore. It's always battery. You have somewhere here, you have the bottle, you have compressed hydrogen bottle.
We need to have a fuel cell for the point.
Yes, exactly. Exactly. So you see, you can have, I think in that case it's 350 bar, and the range could be about 400 kilometer. And you have the fuel electric motor here, the fuel cell stack is here, etc., etc. You must have some lithium-ion battery. That's a very important point. You must have always battery, particularly for a car. And the ratio between the power of the battery and the power of the fuel cells could be a hybridation ratio. With electrical car, you have only one electric engine and you have two sources of electricity, the fuel cells and the battery. It's different from hybrid drivers.
Have you drive this car?
Not that one, but the class A.
So how is the noise?
No noise.
So you don't sleep while you are driving?
It's dangerous.
Resistance.
It's dangerous. Okay, but in the fuel cell car, the power of the lithium-ion battery, for example, is small. I think it's 15 or less, 15 kilowatt, and the fuel cell could be 80 kilowatt. So the main source of energy comes from the fuel cell, from hydrogen. But you need the battery for what? For cold start, because you have to prepare, to heat a little bit, to have good response, good efficiency. You need also for braking, recover of energy. If you brake, you can recover energy with the battery. So you must have always a storage capacity.
How much is the hydrogen right now in Europe? How much they are selling per liter? Or
It's a good question. It is not. Well, the hydrogen is mainly produced by steam methane reforming. So it comes from the oil refinery and so on, and can be about between 5 and 10 euro.
per liter?
No, per kilo.
Per kilo.
Per kilo. Yes, you can convert it.
Kilo is about 1 kilo.
Yes, sure.
Are you sure? 5 and 10?
No. It's no. It's just roughly.
I think in Germany you have the...
Yes, in Germany, yes, Ludwig.
So the typical retail price of hydrogen currently in German filling stations is around €9.
9 euro
They typically don't charge since they don't per kilogram.
per kilogram, yes. 9 euro per kilogram.
They typically don't charge since they don't have the right measurement equipment because of how to reliably measure the hydrogen transport.
Okay, so you have an industrial, but it's not very well developed because it's not mass production, but roughly it's between 5 and 9 and 10 euro per kilo. So that's another nice example for the
Transit bus.
Olympic Games. There was a transit bus, very nice bus with 200 kilowatt fuel cells. I went to that bus, I did not drive it, but I went. It's a very nice bus also. It was used for the athletic people to go from one place to another. And in the yes, okay.
Excuse me,
Yeah.
how many kilometers you can drive by that 1 kilogram?
Normally, for a car, you can get 100 kilometers per kilo of hydrogen. 100 per kilo of hydrogen, more or less. For a bus, more, of course. You need more hydrogen for the same distance, or less distance for the same amount of hydrogen. Yes, sure. But roughly, if you have good fuel cells, 1 kilo of hydrogen is about 100 kilogram for, I would say, a common compact car like Class A or Class B or Class A. Yes. Normally, you have 33 kilowatt-hours per kilo of hydrogen. So 1 kilogram, theoretically, 1 hour, 1 kilowatt, you have 33 kilowatt-hours. But you have to take into account the efficiency. So divide by 2 at least. So 1 kilo could be 10 kilowatt-hours. And you have to include the weight of the storage, the tank. compressed hydrogen. So these example, they have compressed hydrogen pump. So 350 bars, it's more or less common. And now they are trying to have 700 bars to increase the quantity of hydrogen in the tank. With 700 bars reach about 5-6% weight storage. So for 6 kilo of hydrogen, you can get 600 kilometers, and you have at least 100 kilos of tank. More or less.
But for this B-class Mercedes, there was around 7-8 kilograms of hydrogen or something like that.
Yeah, no, a little bit more, a little bit less, like 5-6.
So what makes the hydrogen work more effectively or efficiently? Is it goes from one model to another? You can find some variation.
You mean for the car?
What other parameters that affect the distance?
That's the efficiency of the fuel cell.
Yeah.
Its efficiency will depend on how you prepare the membrane electrode assembly. For example, Toyota, they made good progress in the membrane electrode assembly. So you have better characteristic. I try to show you that if you increase the characteristic of the membrane electrode assembly, you have much energy, much power, much energy converted, much power, much efficiency, etc. So that's the trick. The main point is the membrane electrode assembly. If you are able to make good membrane electrode assembly, you have a good characteristic. Okay, other example, the space shuttle, the alkaline fuel cells. We have also.
Why is it still covered?
Pardon me?
Why is it still covered? It's still covering it. This is long ago. No, the sticks they have covered on the
Stick?
No, can you bring back the picture? The previous one. The previous one.
Yes. No, the stick is not working.
Power meaning.
No,
They have covered. They don't show the.
no, excuse me.
Wikipedia picture.
Yeah, this one. Why is
This-
it covered? The cover, the cover in the front. There's a cover.
Here.
The heat management.
No, the white color. This
White
cover.
color.
They cover it, right?
Yes, that's
I thought no more. It's not a secret anymore.
no.
It goes to shuttle, it's space.
Yeah,
Melt
no,
down.
I think there are some
Protect.
protection for the fuel
the
tank.
heat.
Maybe the fuel cells, maybe it is inside.
I thought they didn't want to show it.
Yeah. Okay, now I have to go a little bit faster, excuse me. Just also for auxiliary power unit for aircraft or for space. So that's interesting point. Airbus is making some experiment, particularly with DLR in Germany, for example, for taxiing on the plane at the airport. Instead to use kerosene or the jet oil turbine at the rear of the plane, they put in the front a small fuel cells, 12 kilowatts, and you can displace the plane in the airport, which is called taxiing, with the fuel cells. So it's a good example. Okay. I am sorry, the stick is no more working because that's a problem of again battery. So you have application to portable electronic, a few watt, 200 watt. Okay, you have a laptop computer, cell phone. It works now? Okay.
It's working.
No. Okay, so I just show you here what we made with cellular, our energy, atomic energy conversion plant.
Direct it to the laptop.
No, get closer to the laptop.
No. And you see that you can deposit the element of the fuel cells on the silicon chip. And with the microelectronic process, we can make micro fuel cells which are able to power cell phones or laptop computer. So it's another application.
MIMS application.
Yes, MEMS.
Is it microfluidic?
Microfluidics, of course. Yes, for example, Samsung in South Korea, they developed fuel cells for laptop computer. Yeah. Okay. So just to summarize all the application of fuel cells, and in this diagram, I just mentioned, I was the director of research grouping in France, which is GDR, Groupe de Recherche, on the fuel cells. I mean of low temperature fuel cells and high temperature fuel cells. And it is an academic grouping, and the aim was to make different research teams to collaborate on this field. It was very difficult because you must have electrochemist, mechanical engineer, you must have thermal management, etc., etc. And we succeed finally to have about 50 teams working together, mostly from CNRS. CNRS is our National Research Center, and some of Atomic Energy Commission also. And also we include some industries now. We are trying to attract industry people like Air Liquide. Air Liquide, they are very interesting. Or Areva. Areva, also they are very
active.
Very active. Okay, so just to summarize that you can have all this wide power range from few milliwatt with biofuel cells to megawatt for stationary power. You have transportation, you have some bike, you have the aerospace, and you have portable electronics. Just to summarize. Normally, after that, I have reference. This is important for you to have books, textbooks.
Any latest book which combine all?
Yeah.
Some of it old literature.
Yes, but all books are good. Huh?
What is your book?
I have no book. I have some chapter in some books. Okay. For example, this one, Frano Barbier, is a good book. I can recommend. Frano was involved in the beginning of this summer school in Aichett. Okay. Okay. Normally, I have to condense my two presentations in one. So I just go to the next one, give you just some idea about the catalyst and the electrocatalyst, which is one point for the PEM fuel cells. You have to develop good electrocatalyst. And I will stop in about less than half an hour. So it will be okay, I think. Okay. Yeah. Yes, I know, but I am very flexible. I can continue during lunch. Don't worry about that. Don't worry. No, I know.
That's why you should have a book. So you don't need fear.
Open. I don't know if it works. Yes. Okay, we discuss a little bit more the electrocatalysis, because it is an important point. So you see again this equation, which is the main equation for the current density versus electrode potential or versus the over voltage, and we make the separation with the chemical part, which is included in the exchange current density G0, and the electrical part, which has the over voltage, exponential of over voltage. Okay, so you can see with this graph, if you make the Arrhenius law or activated complex absolute theory for the kinetics of chemical reaction, you have the initial state, the final state, and you have the barrier. To go from the initial state to the final state, you have to overcome the energy of the barrier. Normally, if you have a spontaneous reaction, the final state must be lower in energy. Okay? in electrochemistry, we can change the relative energy between the initial and final state by the electrical energy. So you have here the electrical energy, number of Faraday, times the cell voltage. So with this E, cell voltage, you can vary the barrier, or you can change the final state in both directions. You can decrease or increase energy. If you increase the energy of the final state, you can reverse the action, because the initial state will be lower. So you can see that with the electrochemical energy, electric energy, you can change the direction of the reaction. This is very important. So you can do any reaction you like to do with the right electrons and the right potential. Okay, now if you see the effect of the electrical energy on the barrier, the initial state relatively doesn't change, the final state changed by NFE, and the intermediate state, the activated complex state, will be changed by the fraction alpha of electrical energy. So the alpha is a transfer coefficient, and you can understand it plays on the barrier height. So alpha is a fraction of the electrical energy which will favor the forward reaction. Usually we take oxidation range. And 1 minus alpha will favor the backward reaction. For simple kinetics, first order kinetics, one simple reaction. I mean one single electron transfer reaction. In reality, it is very, very different. So now the effect of a catalyst is clearly seen here. The catalyst will decrease the height of the barrier. For the chemical reaction between these two states, will decrease by the K factor, which is included in this exponential factor. So by decreasing the activation, the chemical activation energy by K, you will increase the rate by exponential K over RT. So you see the effect, quantitative effect of the catalyst. And for electrocatalyst, for electrochemical reaction with catalytic electrodes, you combine both effects. So you decrease the barrier by the catalyst, and you decrease the barrier by the electrode potential. So this is electrocatalysis. Electrocatalysis is a mixture of heterogeneous catalysis and electrochemical activation. The most point is the effect of catalyst is included in delta G0, that is, in the exchange current density. Okay, I will go away, or that. That preparation of catalyst, I switch off. We will have, I hope, the documents. Well, it's a lot of work to make good catalyst, but I screen. Okay. No, I am very flexible with your time. I can speak about all the day because I am very fond of that, but I am very flexible, don't worry. Oh, look at this one. Oh, you see this nanoparticles? 2 nanometers. It is really nano catalyst. When you speak about nano, you must be in the nano scale range. Otherwise, it's not nano. Some people speak about nano, but it's a few micrometer. That's that. Yes, but you see that at the scale for the platinum cobalt mixture, you have very, very nice crystal, and you see the distribution of size at about 2 nanometers. So we are able to make control particle size, with control atomic ratio between between platinum and the co-catalyst, and we also control the loading.
So what would be the platinum loading here?
For example, just the characterization. I will show you later.
Okay.
But that's for oxygen reaction. Platinum nickel, platinum cobalt are very good. Okay, that's a different kind of preparation of platinum bismuth and so on and so on. But you see, for example, again you have nice particles and evolution of the size from pure palladium to pure gold, with palladium gold electrodes, continuous evolution, because we have a true alloy, with gold and platinum. Okay. So just now, the most important point is the effect of the main reaction involved in fuel cells. So one of the main reactions, of course, is the hydrogen oxidation. In this graph, you have the exchange current density, the logarithm, versus the metal hydrogen bond energy. And you have the mechanism. So just now, to give you some idea, even for the most simple reaction, you have a mechanism in different steps. You have the dissociative hydrogen adsorption, so interaction of hydrogen with the metal, with the catalytic metal, and you give this image adsorbed species, and you have the image bond strengths which arise here. And you have the electrochemical transfer between adsorbed species, giving proton, electron, and you liberate the metallic sheets. So you can write the rate of each reaction. You can including theta, the number of free sites. For example, theta is the degree of coverage by adsorbed species. So the rate of this reaction is proportional to theta. And when you have adsorption, you must have free sites. So it's 1 minus theta. You can include interaction process, you can include the effect of electrical, and you see, you can guess that you have a maximum when the intermediate reaction have equal rates. When the two reactions have equal rates, you get a maximum, and platinum is good because it is on the top and give you a current density of 10 to minus 3, which is the highest one for hydrogen oxidation. But how to explain that platinum is so good? Don't tell me, because I will be here tomorrow continuing the discussion.
I am sorry. Next question.
Oh, sure.
When you take these atoms, you couldn't see that the rare earth, for example, lanthanum, cerium, deuterium, has never used in the fuel cell catalyst.
Yes.
Why? What is the reason?
Because they are not catalysts. They are used for hydrogen storage, because you can, in this lanthanum compound of rare earth, you can introduce hydrogen, and you have dissociation of hydrogen, certainly less proton, electron, and so on. But there are no catalytic properties. It means it is related to the strength. If you have too high bond strength or too low, you have a very low current density because of this reaction. So
I think iridium is almost inhibiting the reaction, or not iridium.
you mean rhenium,
Yeah.
iridium?
Iridium, is it inhibiting? No.
No, it's that the platinum group metals. They are, most of them are active. Okay, experimental results with different preparation, and now you have the quantity of metal loading. You have three curves with different preparation. Most we have 0.35 milligram of platinum per square meter, and in both anode and cathode, the best results you see can get 3.5 amps per square centimeter, can get 1.2 watts per square centimeter, so it's good results. So experimental results, and we also developed some other process by DVD, physical vapor deposition with plasma enhanced physical vapor deposition, so we can deposit just a layer of platinum at the catalyst support and carbon, and you can reuse the mount.
Use what carbon paper?
No, it's carbon vulcan. The
But
normal.
the substrate.
Yes.
Is it fabric or paper?
No, it's a carbon powder. So we get 0.1 milligram, and that's sufficiently for the hydrogen oxidation, but not enough for oxygen reduction. Okay, CO has also one molecule which is involved in the reformed gas. If you take, for example, natural gas, you transform it to hydrogen-rich gas, and you have some trace of CO. So CO is a very bad poisoning species. For example, on pure platinum, if you look at the current density versus electrode potential, you are obliged to go to very high electrode potential to oxidize CO. So all that is blocked. So no current. So you have some CO in the fuel cell gas, the reformed gas, your side will be blocked, completely blocked.
What is the concentration of CO that will make?
Well, in that case, I think it's CO dissolved in the bulk electrolyte. It's a relatively large amount. Okay, but for fuel cells, by fuel cells you have to be below 10 ppm. I will show you later. Okay. So if you have a different catalyst, including platinum ruthenium, platinum tin, you shift the oxidation action towards more negative potential, so you decrease the voltage, so you have better behavior. And again, you can write the different steps, and there's a relatively complicated reaction. Experimentally, you see the effect. That's a cell voltage versus current net stickers from Mukherjee, with pure platinum ruthenium, and platinum tin deposited on the carbon like a Vulcan XC72, and the effect of a small amount of CO, 5 ppm to 100 ppm. You see, on pure platinum, 100 ppm, that's a very bad electrode, is completely blocked, but with ruthenium and tin, you improve the characteristic. Okay? Experimental result with platinum electrode and platinum tin. Platinum tin is a good behavior. So you have a negative cooperation between ETEC, platinum tin 3:1 atomic ratio, and platinum tin we prepare in our laboratory. You have the conditions, the loading here, and you see that with platinum tin prepared in our laboratory, we get better results in the case of the presence of CO here. You have 100 ppm of CO, and with this platinum tin 20% or 30% metal loading, we have a relatively good result. Relatively. But you decrease the performance, of course. The last point, the oxygen reduction reaction. This one is terrible for the fuel cells, because most of the voltage occurs at this electrode. It is because the mechanism is complicated. The more complicated is the mechanism, the higher is the difficulty to make the reaction, and the voltage is high, the current stays down. So you see, you have direct formation of water, or you can go through hydrogen peroxide, and you have different steps. If you go a little bit further, you have absorption of oxygen, then you have first transfer of electron with proton, and when you have O2H adsorbed, there is two pathways. Either you have a second addition of proton and reduction with electron going to hydrogen peroxide, or you can continue with absorption of the species, and you cleave the OO bond. So the main point for oxygen reduction is to break the OO bond. And to break the OO bond is a very difficult process. There are many catalysts which were tried to do that. If you break the OO bond, you can continue the reaction, and finally you get water. So we have to make the overall reaction with 4 electrons going to water, because that's the most efficient first, and you avoid the presence of hydrogen peroxide, which is a very bad oxidant for the membrane. The presence of peroxide, hydrogen peroxide is very bad. It can damage the membrane. Okay, just to show you. So results, effect of chromium, very small effect. You displace the oxygen reduction towards positive. So you must have theoretically 1.23 volts, it begins here, but because of the voltage it is shifted on the negative direction, and with some platinum chromium, for example this one, 20% chromium, you improve a little bit, but very small improvement. For the cell with platinum cobalt, that's a result for a single cell, and you have also some improvement with platinum cobalt 90-10 or 80-20. Okay. And people were looking for other catalysts, macrocycles. We have transition metal here with 2 oxidation states, and this can be catalyst for oxygen reduction. It's look like in our body with hemoglobin when we reduce oxygen in our body. So it's a biomimetic. But people try this also as catalyst, but there are some results. Not so.
You call it organometallic.
Yes, organometallics. If you compare platinum and iron ferrocyanide, which is a macrocycle, organic macrocycle compound, you have the complete reduction to water, but you have the shift in the bad direction. So you have overvoltage. So it's not so good. But one point is, if you have a methanol fuel cells, these macrocycles are insensitive to the presence of methanol. If you have crossover of the alcohol through the membrane, you don't modify the characteristic of the cathode. So it is interesting from that point of view. And finally, some with the dark methanol fuel cells, some voltage versus current density, power density versus current density curves. It's not so bad with ferrocyanide dispersed in polyaniline, which is a electronic conductor, and at room temperature you can get 6 milliwatts per square centimeter, which is not so bad. Okay, that's some conclusion about that.
Very good.
I think I am in time. So you see the conclusion. Conclusion is there's a lot of fun because there is a lot of difficulty. The more difficulty you have, the more fun you have. If you have no difficulty in your life, no fun. For fuel cells, there is a big challenge. You see that we must reduce the quantity of platinum, because platinum is a tricky material. It works. It works for many reactions. You have to increase the amount of platinum below 0.1 gram per kilowatt. So if you can get 10 kilowatt per gram, it would be nice. 50 kilowatt, 5 gram, no more, not much more than exhaust was catalytic exhaust of our car. The other point?
So which is how many percent of the total cost?
Oh yes, that's a good question. I don't answer. The second point, the oxygen reduction. So that's a very difficult action because we have 4 electrons per molecule. So the more electrons you have, more difficult it is. So we have to decrease the overvoltage because it's too high. You imagine if 0.4 volt overvoltage due to oxygen reduction reaction, it's a loss about 1/3, but 33%. 0.4 over 1.2 needs 33%. So 33% of energy, 33% of power is lost because of the oxygen reaction. So the main point to develop 10 fuel cells and to find that it is just a dream, a good oxygen reduction reaction. But because it is a dream, it's a good for students. because the students, they are young people usually, they still dream. So they can dream a long time about oxygen reduction reaction. And those who solve that problem will get the Nobel Prize. And I'm sure about it. And the point I put that the results of CO also, if you have a reference gas, you must deal with CO. Okay, again, you have some references. They are not much more complicated. And then some acknowledgement. And thank you for attention. Thank you very much.